Welcome to this bonus lecture intended for my statistics students about the power of a statistical test. This lecture is more advanced than what we'd usually cover in class, but hopefully it'll be interesting and help you understand the goals and drawbacks of hypothesis testing a little more clearly. Let's review the critical definitions of type 1 and type 2 errors because we'll use these ideas a lot today. If we fail to reject the null hypothesis, that's the correct decision if the null hypothesis is true, and it's a type 2 error if the null hypothesis is false. That means we should have detected a significant difference, but we didn't. If we reject the null hypothesis and conclude the alternative hypothesis, that's the right thing to do if the alternative hypothesis is true, but it would be a type 1 error if the alternative hypothesis is actually false. By notation, the probability of committing a type 1 error, we write it with this alpha, the significance level, and the probability of committing a type 2 error, we call this beta. Now, hypothesis testing assumes the test is set up correctly, so H0 being true means the alternative hypothesis is false, and vice versa. They cannot both be false. Make sure you don't use a one-tailed test if it's plausible that the true mean is higher than or lower than the assumed value in the null hypothesis. Now, some examples of these. In academic research, false positives or type 1 errors are more common due to the publication bias and p-hacking, like cherry-picking data until non-significant results become significant. And then in medical testing, type 2 errors, false negatives, are more common if tests lack the sensitivity. You actually have the disease and your mark might be off the charts, but the test didn't say it was. I have an example for you to start us off. So the IQ is normally distributed with standard deviation 16. We use a sample of 64 people to test if the population mean that the sample generalizes to is 100 or higher than 100. If we decide to reject the null hypothesis, if the sample mean x bar is larger than or equal to 103, what is the probability of making a type 1 error? Well, if H0 is true, the IQ of one random person, if we have a mean of 100 in the population, will be normally distributed with the same mean 100 and the given standard deviation sigma of 16. Now, if we take the average of 64 people's IQs, the average is going to be much closer to the center. In fact, the standard error will be 16 divided by the square root of 64, so the new standard deviation will be 16 over 8, which is 2. And so the sample means have this sampling distribution, where the mean is still 100 under the null hypothesis, but the standard deviation of the sample means themselves is much smaller. Now, taking the same picture and zooming in on the x-axis so we could see a little bit better. The first thing we'll need to do to solve this problem is to find what z-score would be a sample mean of 103. So given the sample size is 64, we'll use this z-score formula, x bar minus mu all over the standard error. And so that's 103 minus 100 all over 16 is sigma over the square root of the sample size 64, which boop 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 in the calculator becomes 3 over 2 or 1.5. So a sample mean of 103 would have a z-score relative to all sample means if we took a sample size of 64 people and the true mean were really 100 as the null hypothesis claims. The z-score would be 1.5. 103 is 1.5 standard deviations above the mean. If we decide to reject the null hypothesis if the sample mean is 103 or larger, the probability of making a type 1 error is this area in orange here, because given our sample size, our sigma, and our supposedly true population mean of 100, this area in orange would be reasonable sample means that are larger than 103. So we would falsely reject the null hypothesis, saying the population mean IQ is higher than 100 from our sample being larger than 103 or 103, with probability 0.0668, which is the probability that the z-score for the standard normal distribution is higher than 1.5. So this gives us our alpha, our significance level of 0.0668 for this decision, and 1 minus that number gives us our confidence level of 93.32%. Now let's say we have some new information, that the true population mean IQ is actually 104. Now, using the same decision to reject the null hypothesis if x bar is larger than or equal to 103, what's the probability of making a type 2 error? Meaning, what's the probability of not rejecting the null hypothesis when we actually should? Because we have this information that the real mean is 104. That is indeed larger than 100. So the null hypothesis is false, and the alternative hypothesis is true. So here, if mu is 104 and sigma is 16, we'll have for samples of size 64 this true distribution of sample means that we would observe if we repeated the experiment several times. And so looking at the specific score of 103, that would be a z-score of minus 0.5. You could take 103 minus 104 all over 16 over the square root of 64, and that would give you minus 0.5. And so the sample mean IQ 103, where we would make our cutoff in our decision, with a sample size of 64, would have a z-score of minus 0.5 compared to all samples of size 64 that we would actually get if we have a true population mean IQ of 104. So this means all these realistic samples that we could get up to 103 would not be considered enough evidence for us to reject the null hypothesis, even though we should. That would be a type 2 error, and so the type 2 error happens with probability equal to this area in green. A sample mean below 103 would not make us reject the null hypothesis, but that really happens with the true population mean mu of 104, with probability that the z-score is less than minus 0.5, which is 30.85%. Now we're ready to talk about the power of a test. It is the probability of not making a type 2 error, meaning if the alternative hypothesis is true, the power of the test is the probability of rejecting the null hypothesis and correctly claiming the alternative hypothesis. So here, because before we had beta, the probability of making a type 2 error of 30.85%, the power of the test is going to be 69.15%. So if we're going to reject H0 for all the sample means 103 or larger, if the true mean is 104, and the sample size is 64 and the standard deviation is 16 for individuals, we correctly reject the null hypothesis with probability of z-scores being larger than negative 0.5. And that is exactly 0.6915. You could also take 1 minus beta and get the same exact value. So that's great. Now we know the power for mu is 104. What if instead the true population mean IQ was equal to 108? How would that change things? Well, first of all, the distribution of sample means that we would get if repeating the experiment several times is shifted over to the right to have a new mean of 108. So that might change the area significantly if we're using the same rejection decision of the sample mean being larger than or equal to 103, because now 103 might have a much smaller z-score. In fact, we can calculate that z-score exactly, so let's do that using the same formula. X bar of 103 minus 108 all over 16 over root 64. We're still using samples of size 64. that would give us a z-score of minus 2.5. So the sample mean IQ 103 of a sample of size 64 would have a z-score of negative 2.5 compared to all samples of size 64 we would expect to get if mu were really 108. So here's our z-score of negative 2.5. As you can see, it is a much larger area in orange. That is the probability of not making a type 2 error or of rejecting the null hypothesis when we really should. So the power is this orange area, the probability that the z-score is larger than minus 2.5, which is 99.38%. Now, because we have our power, we can also answer another important question. What is beta, the probability of committing a type 2 error? Well, it is exactly 1 minus the power. And so the probability of committing a type 2 error, beta, is 0.0062, or about 0.62%. So to put this into context of the problem, this means if the true mean IQ were indeed 108, and we took samples of size 64, we would get a sample mean of less than 103 about 0.62% of the time, and because of our rejection region decision, that would not be enough to reject the null hypothesis, which would be an error because if the true mean is 108, that certainly is more than 100, so the alternative hypothesis should be our goal. But we won't reject the null hypothesis with probability 0.0062, and that is also the probability of making a type 2 error. That is beta. Let's talk about another problem together. Using a significance level alpha of 0.05, we are testing if the mean adult male height in the United States is equal to 70 inches, that will be our null hypothesis, or not equal to 70 inches, that will be our alternative hypothesis. So assume heights are normally distributed, use sigma of 5 inches for the individual, and a sample size of 100 people, 100 adult males in the US that will be testing their heights. What is the power of the test if the true population mean is actually 68 inches for adult male heights in the US? So if H0 were true, the sample means would be distributed according to a normal distribution with mean 70, that's what we're assuming with the null hypothesis, and standard deviation 5 over the square root of 100. So the sample means themselves have a much smaller standard deviation of just 1/2 because we have 100 people being averaged together. So if there are outliers, there should be as many above and below if it's normal. So we will get much closer to 70. And then if the true population mean is mu, general mu, not necessarily the mu 70 given in the null hypothesis, then the sample means we get will be distributed according to a normal distribution with mean mu now, general mu, and the same standard error 1/2. For a two-sided test, because we are indeed testing the alternative hypothesis that mu is not equal to 70, so it could be larger or less than 70, just not equal. Alpha of 0.05 means we reject the null hypothesis if for draws from z less than or equal to 0.025 or z is larger than or equal to 0.975. So we'll be rejecting 2.5% of the area on the lower end and the higher end. Now remember, hypothesis tests work by assuming the null hypothesis is true, which in this case will assume mu is really 70, and then getting an unlikely result as evidence against that. So we'll get sort of a contradiction. Recalling that z of 0.025 is 1.96, so there is a z-score of 1.96 that has 2.5% of area above it under the standard normal curve. We will reject the null hypothesis if the sample mean is in this interval here, so an interval notation. This is all the values that are less than 70 minus 1.96 standard errors. And then we'll also reject the null hypothesis if we're larger than 70 plus 1.96 standard errors. And so this is, if you were to calculate it, all the values that are less than or equal to 69.02 or above 70.98. So if we got a sample mean that was 71, that's in this part here, so we will be rejecting null hypothesis. If we got a sample mean of 69.85, that's not in here, so we wouldn't reject the null hypothesis. If we got a sample mean of 4, that's super way down there, and we would reject the null hypothesis, for example, some values to put in. In other words, here is where we would reject the null hypothesis. Notice these bounds right here, 69.02 and 70.98. That is the 95% confidence interval for the sample mean. So if the sample mean is outside the 95% confidence interval for that sample mean, assuming our null hypothesis mu of 70 inches, standard deviation of 5 inches, and a sample size of 100, then we will reject the null hypothesis. So now that we've set up the problem in our minds, remember our test setup will be rejecting the null hypothesis if the sample mean is in these intervals. If the true mean were 68 inches, 69.02 as the sample mean with 100 people would have a z-score of 69.02 minus 68 all over 5 over root 100, which is 2.04. And similarly, 70.98 as the sample mean would have a z-score, if the true mean were 68, of 5.96. That's extraordinarily high. So to draw a picture, here is in red, the distribution of the sample means we would expect to get if the null hypothesis were true, if the mean really were 70. In green, here are the sample means we would expect to get if the population mean were actually 68 inches instead. And so as you can see, we have our z-scores, 0 standard deviations above the mean, 1 standard deviation above, 2 standard deviations above. 69.02 has a z-score of slightly more than 2, that's 2.04, so that's why we see this cutoff here. And then also, it's hard to see, but we also have a cutoff at 5.96 standard deviations, where we would still be rejecting the null hypothesis, because remember, the null hypothesis will be rejected if mu is not 70 inches. It doesn't necessarily have to be less, it could be more. So if we have a sample mean above 70.98 inches, then we will also reject with this adorable little area on this side on the right. Okay, so the power of this test is the probability of z-scores being less than 2.04, because if we get a z-score of less than 2.04 with a true mean of 68 inches, we would be rejecting the null hypothesis with this test. And we could also add the probability of z being larger than 5.96. That one's very small, but the probability of z being less than 2.04 is quite significant. That's 0.979325. And so adding those together, we get the power of the test, the probability of not making a type 2 error, of actually rejecting the null hypothesis, given the truth that the true mean is 68 inches, would be 97.9326%. So there's a small chance that we'll make a type 2 error, but there is a very large chance that we won't. That seems great. Let's talk about the goals of hypothesis testing. The most important goal is to find the truth, so we'll try to minimize errors in the test as much as possible. So first, we want to minimize the probability of committing a type 1 error. That probability is exactly alpha, the significance level, and alphas of at most 0.1 are typical in studies nowadays. In some fields, it's even more strict. We also want to maximize the power, which means we want to minimize the probability of the type 2 error occurring, which happens with probability beta. Okay, so power being larger than 0.8 as usual. This means because beta is 1 minus the power, beta is at most 0.2 usually. But now here's an important question. We don't actually know the true population mean. Otherwise, we wouldn't be testing for it, right? So how do we find the power? Well, the answer is that we actually find the power for all the possible population means, and this will be seen in a power function. Now let's understand these power functions together. So the power of a hypothesis test depends on the value of the true population parameter that's being estimated with our sample statistics. If the actual mean mu moves farther away from the hypothetical mean mu0, the power of the test increases. Remember, in our IQ example, the hypothetical mean was 100. If we had 108 as our true mean mu, we had a much larger power than we did when we had a true mean of 104. I have an example for you. Let's say we were testing the null hypothesis that the true population mean is 13 against the alternative hypothesis that the true population mean is strictly less than 13. We'll test this with a sample size of 9 individuals at a significance level of 0.1 with a population standard deviation sigma of 1. So recall z of 0.1 is 1.28, so we'll reject the null hypothesis if the sample mean we get is less than 1.28 standard deviations below what we suppose is the mean. So that will be our rejection region, all of the sample means that are less than 12.573. So if mu were 12.5, in fact, not 13, then our sample means would come according to this distribution in green. And so the z being less than, let's find out what this number should be. 12.573 minus 12.5 all over the standard error. It looks like 12.573 has a z-score of 0.219. If the mean is 12.5 and the standard error is 1 over root 9 or 1/3. So let's find out how to handle this. We have this wonderful region here in green. It looks like these are all of the sample means that we would get if the true population mean were 12.5. So all we need to do is find this area, and that will give us the power of our test. So here, the probability that the z-score is less than 0.219 is 58.7% or 0.587. So 58.7% of the time, if the true mean is 12.5 and we have everything else as above, we would reject the null hypothesis because that is all of the sample means we would actually be getting. We'd get all these sample means that are in the rejection region. But we can do even better. What if mu were actually 12? The true population mean were 12, not 13. Then we have even more sample means that we would expect to be in the rejection region. In fact, a z-score for this value of 12.573, if the true population mean were 12, and we have a sample size of 9 and standard error of, let's see, 1 over root 9, would be 1.719. So we will have a power, we'll be rejecting the null hypothesis 95.7% of the time. The probability that the z-score is less than 1.719 is 95.7%. And so here we would get sample means drawing from this true distribution if the true mean were 12, not 13, and that would be outside of the acceptable values if the true mean were 13 of the acceptable values of the null hypothesis. So we would be rejecting that null hypothesis that the true mean is 13 much more frequently if the true mean were actually 12. Now, if the true mean were actually 11.8, we would reject the null hypothesis even more because we would expect even more sample means if we repeated this experiment several times to be in the rejection region. And so here, if we take this value, 12.573, if we were to find the z-score of that sample mean with a sample size of 9, sigma of 1, and we're looking at a true mean of 11.8, that would have a pretty significant z-score of 2.319. So there would be a 99% chance, in this case, we would have a sample mean that is less than 12.573, which means we would reject the null hypothesis as we should, not making a type 2 error. So we would have a 1% chance of making a type 2 error if the true mean were 11.8. But as you can see, we're able to calculate wonderfully all of the powers depending on what these potential true population means are, all these different mu values. In fact, we don't have to specifically choose certain values. We could calculate this for all values and make a function. So this function depends on the true population mean mu, that will be our input, and the output will be our power. Now power will be from 0 to the highest value 1, but you can see, we'll talk about this formula, but we can see these exact points on this function, and if you were choosing different mu values, maybe like 12.3, we'd get about 0.8. That would be the power if we had a mu of 12.3 and everything else the same. You could see you're able to understand the power of the test given each potential true population mean mu. And you could see all these points are on there. If we have 11.8 as the true population mean, then doing this test, it's very likely that we would reject the null hypothesis that the mean is 13. 99% of the time we'd do that. And then if the true population mean were 12, we'd reject the null hypothesis that the mean is 13, 95.7% of the time. If the true population mean were 12.5, we would reject this null hypothesis that the true mean is 13 about 58.7% of the time. And then think about why, if the true population mean were 13, we would reject the null hypothesis that it is equal to 13 10% of the time. Did you think about it? It is exactly because alpha is 0.10. This power function is a wonderful tool. We could do lots of different things. For example, let's say we wanted a power of at least 0.8. If we had an alternative hypothesis that were true, we wanted some test that would have at least 80% chance of giving us that evidence. So let's say we would check along the y is 0.8 line. When the power level falls below 80%, for this alpha and sample size n given in the problem, the test has 80% power if mu is 12.3 about. So that's something great you can do. You can check specific true population means. You could see how far away from the hypothesis you would need to get a power that is high enough for you to be confident in your result, or confident that you will have enough evidence to show your result. Also, because you're able to compute the power, you're also able to compute immediately beta, because beta is 1 minus the power level. So here, for example, if mu is 12.3, beta is 1 minus 80% the power level, so beta would be 20%, or 0.2 for mu is 12.3. Here it looks like beta would be 1 minus 0.587. That will give us a little bit more than 0.4. Okay, and so then another thing, we previously talked about it, but if mu is equal to 13, remember, the power means the probability of rejecting the null hypothesis given the true mu. If the true mu is 13, we're rejecting the null hypothesis falsely. We're rejecting a true null hypothesis. That is a type 1 error. So that gives us exactly alpha, which from the problem we know should be 0.1, and we're happy to see it exactly is. Now, just in case you need them, I present the general formulas for power functions. These are for z-test for one population mean specifically. You'd have different formulas for other tests, but you can always derive them. So we just looked at this case where we were having an alternate hypothesis of mu being less than some hypothetical value. Then this function k of x that gives us the power for all of our x values, our true parameter mu, for example. The probability of z being less than, here we have mu 0 minus z alpha times sigma over root n, so that would be the critical value, minus x, so the critical value for rejection region, difference from the true mean, all over the standard error, sigma over root n. So we calculated this here, but I want to show you where that came from. We got 12.573. That was the value where if we got a sample mean below that, we would reject the null hypothesis. That is exactly from the test. So that's right from the z-test for one population mean. That's the mu 0, we thought it was 13, minus we tested at an alpha of 0.1, so that z alpha is 1.28, times sigma was 1, over root n, and n was 9, so that would be root 9. This is still minus x all over 1 over root 9. And so that's exactly why we got this function to graph previously in Desmos. And this is how you could plot it in Desmos. You say the normal distribution, you want the cumulative density function up to this value here, so that gives you the probability that the z-score is less than this value. Okay? And so if you have an alternative hypothesis where mu is larger than a value, it would be the probability that z is more than some bound. When notice the difference, we have minus here and plus here. You could also calculate this as 1 minus the probability that z is less than that bound. And then if you have a two-tailed test, the main difference, you have both minus and plus, but also see we have the z of alpha over 2's. So let's say we had a significance level of 0.05. We wanted to reject the null hypothesis if we got 2.5% of the area that's very extreme on the left and 2.5% of the area that's very extreme on the right. For our sample means, assuming we have this mu 0, we have our rejection regions, and we have the whole formula after that. Now, I'd like to point out something I think is quite interesting. We can also compare power functions for different choices of configurations. So, all else equal, meaning the sample size is the same, all of the standard deviations for the individuals are the same, and so on. Increasing the confidence level, which means decreasing the significance level alpha, lowers the power of a test for all choices of mu. So we have this bidirectional situation here. Less alpha means more beta, and also less beta means more alpha. So as one increases, the other decreases, generally all else equal. You can plot the power of a test given each potential true population mean mu with different functions to compare different choices of alpha. Let's see an example of that. It's actually the same exact example as before, but instead of using alpha of 0.10, we'll now use alpha of 0.01. So here we have the rejection region. Z of 0.01 is 2.326, so we need to be a little bit stricter. We'll reject the null hypothesis if the sample mean is now less than 12.225. So here, remember, we're doing this test. When we do a hypothesis test, we assume the null hypothesis, so we'll assume the mean is 13, and then we'll take all the sample means we could get. This is the sampling distribution of the sample mean, and then we're looking what value of the sample mean has a z-score that is 2.326 below the mean. So that is right here, it's going to be 12.225. And so then if we were to calculate the power now, if the true mean were 12.5, the power would only be 0.205. So see, we have a lot more overlap now because this rejection region is farther away from mu, so it's harder to reject the null hypothesis, which might be a good thing depending on the application, but it also means that it is much more likely to commit a type 2 error. See, we have less area now in the rejection region for a true mean that is in fact different than 13. It's less than 13, so the alternative hypothesis is true, but we won't be rejecting the null hypothesis very often. We'll just reject it 20.5% of the time if mu is 12.5. If mu were 12, a little lower, it's a little better. The z-score of the critical value 12.225 as the sample mean is now 675.675 for our mean of 12. So we'll reject the null hypothesis, as we should, 75% of the time. And then if mu is even lower, 11.8, we'll reject the null hypothesis, as we should, 90% of the time. And so you could plot these points I've graphed here. Here was what we had before in blue, the original function where alpha was 0.1. Now for a significance level of 0.01, you notice the power has actually decreased for all the values of mu. We can see these 3 points that are on the graph. For example, 11.8, the power is 0.9. Now for a mu of 11.8, we'll reject the false null hypothesis 90% of the time, but we could do a little better. When we had an alpha of 0.1, we rejected it 99% of the time. So it's important to take this in mind when you're making a decision. But there's still something great we can do to fix this issue. Can we decrease beta, the probability of making a type 2 error, without increasing alpha, the probability of saying we have something when we don't? The answer is yes, by increasing the sample size. So here's an example. Let's test this null hypothesis that the true population mean is 10 versus the alternative hypothesis that the mean is larger than 10 using a significance level that'll stay fixed at 0.05. Remember, z of 0.05 is 1.645 with a standard deviation for individuals in the population of 1. We'll assume there's a normally distributed population, all assumptions needed met. And also, let's say we know, magically, the true population mean mu is in fact 10.5, so we should be rejecting this null hypothesis. It's not equal to 10, it's 10.5. First, let's try using 16 people in a sample and see how that goes. So we'll reject the null hypothesis if the sample mean is larger than 10 plus 1.645, that's z of 0.05, times standard error. So here we'll have our sample mean, the mean of the population is equal to the sample mean here. We'll go up a few standard errors. We'll go up exactly 1.645 of them, and that will make our rejection region cutoff of 10.41125. So if we ended up with a sample mean larger than that, that would be 5% of the time under the null hypothesis that the mean is 10. However, it's actually going to happen a lot more than that because the true mean is 10.5. In fact, this cutoff of 10.41125 has a z-score of all of the sample means we would really get with this true population mean of 10.5. The z-score is minus 0.355. That's calculated here. And so 63.87% of the time, we will be truly rejecting the null hypothesis, which is good. We should reject the null hypothesis because 10.5 is more than 10. But we can do even better. Let's say if we had a sample size of 100 rather than 16, this changes a few things. First of all, if we have a sample size of 100, we expect the sample means to be even closer to 10 under the test. We expect the sample means to be even closer to the null hypothesis value, mu of 10. And so that will already help us. This means the rejection region will have the cutoff at the sample mean 10 plus z of 0.05, that's 1.645, times the standard error is now 1/10 rather than 1/4. So you see this is already going to be much closer to 10. It's 10.1645. And so looking at this picture here, we see almost all the values that we will actually get are outside of this acceptable range. We're in the rejection region for almost all of the sample means we'll get. So we can compute the power explicitly. First, we find out now this cutoff, 10.1645, has a z-score relative to the true mean of 10.5 and samples of size 100. The z-score of that low of a sample mean would be minus 3.355. That's calculated here. We do the value minus the true mean, 10.5, all over the standard error. That's how many standard errors above the mean we are, but since it's negative, we're below the mean. Okay, so then we'll take the 1 minus the probability that z is even lower than that. It's very small. We'll get 99.96% of the time. We'll be rejecting the null hypothesis, as we should. And so the power of this test is 0.9996. Notice we did exactly what we were trying to do here. We decreased beta, increasing the power, while keeping alpha the same. Notice it was 0.05 for both. We had it here and here when determining the rejection regions. And all we did was we increased the sample size. We had the same standard deviation. We had the same test we were setting up. We had the same true population mean. We didn't have to change anything but the sample size. Here's what it would look like to compare the power functions. If the test is set up correctly, meaning for us, mu is only 10 or larger, it shouldn't be less than 10, increasing the sample size decreases type 2 error risk, even without changing the type 1 error risk alpha. So here we see both curves. This is the power function for n equals 16, and we saw our exact point when the true population mean was 10.5. We had a power of 63.87%. Here in purple is the power curve when n is 100. That increased the power for many, many values that we would expect to get, but we saw it exactly for a true population mean of 10.5. That changed the power up from 63.87% to 99.96%. So as you can see, that's a significant decrease in type 2 error risk. That's an increase in power. And remember, type 2 error risk, this beta, is 1 minus this power height. So here it used to be all this. Now it's just this tiny itty little bitty spot, 0.0004. So it's a great thing in this case to increase the sample size. And then I just want to point out, it actually decreases for mu less than 10. The power decreases, but we should not use a test that mu is larger than 10 if it's possible or reasonable that mu is less than 10. If it's reasonable that mu is less or greater than a given value, you should use a two-tailed test. Now this makes me wonder, if increasing the sample size and changing nothing else can increase the power, then maybe if we have a goal for the power, we can compute the sample size we'd need exactly. So let's see an example where we do just that. Wild dolphin lifespans are said to be normally distributed with a mean of 28 years and a standard deviation of 5 years for individual dolphins. But we think the mean is actually 30 years. To test this with a significance level of 0.05, meaning we'll test at 95% confidence, and have a power of at least 90%, what sample size should we use? So first, this alpha is 0.05 condition. We'll assume the null hypothesis, doing our regular test, and find the critical value for our regular z-test, okay? So c will be 28 plus z of 0.05 times the standard error. Here that would be c is equal to 28 plus 1.645 times 5 over square root n. Now the only thing we don't know yet is this n, but we'll be able to solve for it because we have another condition. We also know if we want a power of at least 90%, 0.9, then beta 1 minus the power should be 0.1. So if it is truly 30 years as the true population mean, then the critical value for that side, which we'll visualize soon, will be c equals 30 minus z of 0.1 times the standard error. So we should be 1.28 standard errors less than 30. If 30 is the true value, that should be the critical value we're considering for 90% power. Okay? And so setting c values from both conditions equal, and then solving for n, always round up to a higher n, of whole number n, we'll have this first piece here, 28 plus 1.645 standard errors, is equal to this second piece because we're finding the critical value c that makes both of these conditions hold. And then solving for n, we can add 1.28 standard errors on both sides and then subtract 28 on both sides to get 2.925 standard errors. 5 over root n is standard error, is equal to 2. And then we can multiply both sides by root n and divide by 2 on both sides, so we get root n is 7.3125. Then we'll square both sides, so n is 53.47 about, so we'll round up to n of 54. Now let's check everything. Putting in n equals 54 to either formula of this critical value c, we get a cutoff, a sample mean of 29.1193 years. So here we'll check both conditions. Here we have in red, in both pictures actually, the sample means if the true mean were 28. So we'll have, since we're testing if it's higher, then we'll have this rejection region with 5% of the area above it. And then we also have here this same rejection cutoff showing that for sample means, if mu is actually equal to 30, 90% of the data, 90% of the sample means we get if we were to repeat this experiment many times with samples of size 54 would result in a rejection of the null hypothesis, which is correct because if the true mean is 30, we should be rejecting the null hypothesis that it is 28. So just to quickly review what we did, we found a cutoff point C that if the true mean were 28, 5% of the area would be above it, 5% of the sample means we would get with a sample size 54 would be above it. We found that 54 specifically to give us that 5%. We also found C such that if the true mean were 30, 90% of the area would be above that value. So we would be rejecting the null hypothesis 90% of the time. That's the second condition. We also found the n needed for that. Together, we found the conditions that are met, both of them, for n is equal to 54. Now, I just want to point out, if you increased n even more after 54, up to like 100 or 1000, this won't be an intersection anymore. So you would need to choose one of them as your critical values. Probably if you're doing a standard test, you just choose this top one. That would still give you an alpha of 0.05, but your beta would just keep decreasing as you increase n and use the same alpha equals 0.05 condition, where your cutoff would be 28 plus 1.645 times 5 over root n, which as n increases, you'll be dividing by more and more, so this cutoff will get closer and closer to 28 as n increases. But also as n increases, you'll very rapidly get a great power for your test. For example, if you got up to a sample size of 100, you'd already have a power above 99%, up from 90%. Now, since we already did this computation, I want to share a shortcut formula so you don't have to do this computation over and over again. Now you can just put in your z-scores for your alpha and beta that you're willing to accept, then your sigma, your population standard deviation, or at least a very good estimate for that in practice, mu 0, what people think the true mean is, and mu, what you suspect it is, possibly with some pilot data, for example. So here, if you're doing n, round up z alpha plus z beta, all of that times sigma, all over mu 0 minus mu, and then square the whole thing. So round up that amount. Here for us in this problem, z alpha, we wanted an alpha of 0.05. So z alpha will be z of 0.05. That's 1.645, the z-score with 5% area above it in the standard normal distribution. Z beta is z of 1 minus 90% because we want a power, let's say, of 90% here. So that's z of 0.1. That's 1.282. In the problem, we're given sigma of 5, mu 0 of 28, and we think mu is 30. So for this, we should round up this specific value. Here we have all of our data inputted. Here we go. And then we square it. We'll round up to get 54, and you can check if you'd like. It's the exact same as we got in the previous slide because it's the exact same problem. Now I have a challenge example for you. In this one, unlike the rest of the lesson, we'll be talking about sample proportions rather than sample mean. So now we'll not be thinking anymore about the standard deviation of the individuals, because now we have the standard error square root of p hat, or some estimate for the proportion, times 1 minus p hat all over n, rather than the previous square root of sigma over n. So here's the example. People think 50% support candidate A in some election, but we think it's maybe 45%. To test at alpha equals 0.01, so a 99% confidence level, and to have a power of at least 80%, so a chance of detecting a significant difference, rejecting the null hypothesis when we should at least 80% of the time, what sample size should we need? So first, let's use the condition alpha is 0.01. We'll do our regular test for one population proportion. We'll assume the null hypothesis that the proportion is 0.5. and then we'll find the critical value. C is 0.5 minus Z of 0.01 standard errors. And then we'll use beta is 0.10. If P is actually 0.45, if that's true, then the critical value would also be C is 0.45 plus Z of 0.2, because we want 80% power, standard errors, but where our proportion estimate is 0.45 now rather than 0.5 as it was before. Setting the C values from both conditions equal and solving for n, remember always round up when you're using sample size. 0.5 minus 2.326, that is Z of 0.01, standard errors is equal to 0.45 plus Z of 0.2 is 0.842, standard errors for the estimate of 0.5. So see, we have 1 minus P will give us 1 minus 0.45, which is 0.55. And so then we could set these equal and try to solve for n now. Subtracting 0.45 on both sides gives us 0.05 on the left-hand side. Then I'll add over 2.326 standard errors for an estimate of 0.5 on both sides. Now 0.5 times 0.5 is 0.25, so I have the square root of 0.25. And then this is still over square root of n. Remember this formula, if you have square root of a over b, that's the same thing as the square root of a over the square root of b. And so here I split up the square root of 0.25 over n into the square root of 0.25 all over this square root of n. Okay, and I did the same thing here. So 0.45 times 0.55 is 0.2475, and then I split up the square root as well. Okay, so next step, we would like to solve this for n. So we have the same denominator on both terms. We have square root of n, so we can just combine them and then compute 2.326 times the square root of 0.25 plus 0.842 times the square root of 0.2475. That gives us 1.5819. This is all over root n still. So now we can multiply by root n on both sides, divide by 0.05 on both sides. Then, because we have root n, we want to square both sides. And so boop, 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 in the calculator, we get n of about 1000.96, and we round up to get a whole number. For our sample size needs to be a whole number, we'll use n of 1001. Now let's check it all. Plugging in n is 1001 to either formula for C gives us a good estimate for the cutoff. You could plug in this exact value and get the exact cutoff if you'd like. It is a sample proportion of 0.46324. So if we had, using our regular hypothesis test, testing if the proportion is 50% or not, if it's less than that, then if we got a sample proportion that's less than 0.46324, which will do 80% of the time, then we will reject the null hypothesis in favor of the alternative hypothesis, as we should if the true population proportion is 0.45. And so here I have this graph. We'll have 20% as our chance of committing a type 2 error. That's what we said was acceptable for us. This sample size was exactly fitting both conditions. And also, we still wanted a confidence level of 99%. Indeed, if we have the null hypothesis, if the true population proportion is 0.5, then here is our cutoff, exactly as we expected, 0.46324. That is about 1% of the sample means we would get if the true population mean were 0.5, with a sample size of 1001 would be below that cutoff. So we would reject the null hypothesis when we shouldn't, 1% of the time, and we will not reject the null hypothesis when we should, 20% of the time. We have met every condition we hoped to meet. And as before, I have a shortcut formula to share with you. So here, for one population proportion, use this formula here, where Z alpha and Z beta, just like before, are the Z scores for the alpha and beta you're comfortable with. with that amount of area above. And then use square root of P0, where that's what people think it is, that's what you would have in the null hypothesis, and P1, which is what you think it is, what you maybe have observed with a smaller sample study that you now want to make legitimate with a larger study. Okay, so here we have Z alpha is Z of 0.01, which is 2.326, that's right here. Then we have the square root. P0 is in the problem 50%. In the null hypothesis, we think it's 50%. So 0.5 times 1 minus 0.5 inside this square root. Then plus Z beta. We want a power of at least 80%, so we'll make our cutoff Z of 0.2 or Z score of 0.842 standard deviations above the mean. And so that will be 0.842 right here, times the square root of P1, that's 45% is 0.45, times 1 minus P1, that's the numerator still, and we're still inside a square here. Then we'll still divide by the difference between what people think it is and what we think it is, so 0.5 minus 0.45. We'll square that business, then we'll round it up, and we get 1001, the same exact number as before, as we expected. Great job working through this bonus lecture.